we're going to get to embark on a new but old topic. Hopefully we'll bring some insights to beams today, the next time we meet, the next time we meet, the next time we meet. We're going to be doing beams for a while, okay? And then we'll go and we'll diverge into something else, and then we'll come back to beams at the very end of the class. Okay? But in terms of some logistics and announcements, so I need to postpone due date for session 10 questions again. Okay, so this will be due, we'll make it due Friday by 12:10. Okay, now today's session has 2 questions, and if you look at them, they're worth half a point each. Okay, because they're multiple choice, and I'm going to give you the answers during class. So there's no reason you can't also get those done by Friday at 12:10. All right, so session 11 questions will still be due by 12:10 p.m. on Friday. Okay. This is not a big deal, okay? Now, why am I late? So this is maybe my dog ate the homework. I don't have a dog, so that would be lying, all right? Now, what happened is we've been undergoing ABET reaccreditation, and the results are not official yet, but it's been an interesting experience, and so I've been swamped the last little bit. All right, so thank you for understanding. Fortunately, that coincided with kind of this interesting lull in the assignments. Okay, the exams, I'm not quite sure when we're going to have them back to you. Okay, there are 150 people in the class. That's a lot of people, and the graders are working on them. Okay. I believe everybody who was planning to take the exam took the exam. If for some reason you did not take the exam and for another reason did not send us a message that you didn't take the exam, it would be good to hear from you. Okay, but otherwise I think the format went okay unless you have feedback. Were there any issues on College Ave? I was here. Were there any issues with College Ave? No? All right. Okay. Thank you for participating in, the division of the class, and I hope you had a little bit more space to work. Not that it was the most pleasant experience. It's an exam. I don't know. Does anyone have like an exhilarating adrenaline rush during exams? Like a positive one? No? Come on. Someone must be nerdy out there. Like you feel like you're an athlete going into a 100-meter sprint. All right, it's more like a 5K. Well, maybe more. It depends how fast your 5K is, I guess. But yeah. I mean, does anyone feel like that? I don't know. There's a sadistic part of me, I think, that misses that. I don't get to experience that. But on Friday for ABET, I was cramming. So I was telling my family, oh, this is like studying for an exam again. Anyway. There is a question that has come up on the FEA. So if you could tone it down just a notch, I'm glad you're happy. There's the sounds of joy, not tears of sadness. So that's good. But if we could tone it down, that'd be great. Thank you. So for the FEA assignment, and this is part of the session 10. Okay, there's a question that gives us, or how do you put it? The question gives us a shear modulus, right? Shear modulus G, right? It just gives it to you. How do I get that into Max or any FEA software? Yes, Brennan?
Do p value and then like take a p value that matches to it?
Yeah. So what you're going to do, okay, you're going to use the equation that G is equal to E over 2 times quantity 1 plus nu. Okay? So go ahead and pick, I don't know, pick an E. So you pick an E, an elastic modulus, okay, something that might be, let's just say you pick 200 gigapascals, right? This hypothetically. What do you got to do? Well, then you got to solve, okay, solve for Poisson's ratio. Nu, okay, using the G that you already have. And when you do that, then you can plug in your elastic modulus and your Poisson's ratio. I got, I think, a little whiff of lunch. All right, so today, so moving on, any questions on that? All right. The questions with the gears, okay, I'm working on the videos for them. I understand that you can do them. Like, you can do them if you just go to the 2015 exam, I believe, number 1 or number 2. Maybe it's number 1. No, maybe number 2. But anyway, if you go, I have the reference in there. If you go to that exam, you can solve the problem. I'm still trying to generate the video, and and given that I didn't really cover it in class last time, I feel like we can postpone that due date. Okay, but you can do everything, even if I don't have the videos. And this semester is the first semester I'm working on getting videos for for select assigned questions. All right, so just be patient with me, please. But you can do the work, right? You've got the past videos from past semesters as well. But we're trying to make the class trying to get the class to be satisfactory, I guess you could say. Okay, so what are we going to do today? And this is the first question for Friday, okay? And there are only 2 questions. The other question is also similar to this one. So we hope that by the end of today, we'll be able to have an understanding for calculating the axial twisting along a beam with transverse loading. And no, right? We're not doing the twist really. We'll talk about beams that twist today, okay? But we're not. Just very briefly, it's not really what we're talking about, and you won't be able to do any calculations. All right, so it's not this one. You'll be able to calculate the internal shear force along a beam with a transverse loading. Yes, and you could already do that, hopefully, okay, because you were in statics. So today it's maybe a little bit of a review, and hopefully some new insights. Calculate the internal bending moment along a beam with transverse loading. Yes. Okay, that's something that you also have already been able to do. And we'll talk a little bit about the relationships between a transverse force and a transverse shear force. So why not? Okay. So those will be, to be honest, we will cover that. Yeah, that might wait. So that might wait until session 12 for more detail, all right? But this is the path we are on, okay? No, we'll cover it today. Yeah, we'll cover it today. Yeah, well let's say, let me edit that. We'll say more detail to come. Yeah, we will do that. Distributed transverse force and more detail to come, we'll say. All right. So, what is a beam? If you think of a beam, how would you define a beam? You've spent a whole bunch of time with them, right, in statics. So what is your definition of a beam? What's that? Up in the back, did you have a definition to suggest? What is a beam? Okay, well, I use my hands a lot, so that's fair. Okay, it's this. Does that sound good? Is that what you communicating, right? We're friendly in our communications. Okay, so yeah, I mean, essentially, it is a long object with small cross section. Okay. And so what we say typically is that the length is much greater than the width and the height. Okay? That's how we define a beam. What's it? And it's like, oh, I go home and I see beams, or I use beams all the time. Your house, probably, if it's got a wooden truss and structure, right, it has a lot of beams in it. Okay, even if it's, I don't know, the dorms, they have a lot of concrete. They have steel in them too, right? So there are a lot of beams in our residential or dormitory type life settings. Okay. What's a plate? And that's not on here, right? But what's the difference between a beam and a plate? A lot of math, actually. Okay, that's a bad joke. We won't really cover plates here, but in mechanics, people do discuss the the mathematics and the deformation of plates. But it's pretty advanced, and it's not stuff we're going to talk about here. And some names that might be associated with beams beams. Euler is you're gonna, if you go out into the world and people say things that are technically cool, Euler, all right. I think it's the same one, Euler's method and various different things. He has made contributions to beam bending and those calculations, which we'll talk about later. Timoshenko is a more recent person who's a mechanics expert, and so if you start looking at beams and plates, okay, that would be someone that you might find as a name. Okay. But today we're not really talking about deflection, right? We're not really talking about deflection. We're just setting the stage so that we can relate the internal loads to deflection in the future. So we can relate the internal loads to stress and strain. Okay? So when you did beams last semester, you were thinking, oh, this is the internal force, right? And this is the internal bending moment. Okay? And that was it. And you have some idea that if the internal bending moment is high, okay, that means that there's probably a lot of stress on the material. And so eventually we'll get there. The different types of beams we can consider. Well, point loads are familiar to us. Okay, right? So these are transverse, meaning they go through. They're orthogonal to the axial direction of the beam. We could have an axial load as well, but we're not going to really focus on axial loads and beams because what is that? That is just a uniaxial loaded bar. But when we get to combined loading, you'll have systems where you have uniaxial loaded bars that are also under bending with transverse loads. Okay? Distributed loads, they look something like this. All right? And I drew this distributed force, W, upward just because in our conventions that we're going to discuss, that would be the positive direction for the loaded, for the distributed force. In reality, gravity usually acts the opposite direction, so we often have a negative W when we do these problems. So now we talk about the supports. So those are two ways we can load it. Another way we can load beams is by applying a screwdriver or applying a moment at some location, right? So that's not really here, but I'll just say we can have a concentrated moment externally applied as well for the loading, although I don't have a drawing for that. But for the supports now, these are what we usually consider to be the constraints. Simply supported would be, I often probably am cavalier in saying pin, okay? But it's really a pin roller, Okay, just so that there's not an additional axial force that's created as the beam might deflect downward, right? Then it's kind of elongating, which would then mean that there's axial load being applied at the ends. So we just put that roller there. But you'll see me make mistakes and put 2 pins, all right? But I'm not trying to be slick. I'm just not being super careful. Okay, so that's simply supported, and that can be described in terms of having a couple reaction forces like that. The cantilevered beam is your classic beam on a wall, and then you can describe the external loads on it as such. Okay. That's what the wall does. It provides a reaction moment and a reaction force. If I were to put just a pin on this end, that would obviously mean that the beam just can spin, right? And that's a problem. So a cantilever beam needs to have a reaction moment. It needs to have a supporting force. An overhanging beam can be something where essentially we have a wall constraint and we have a roller constraint, or some type of, again, I would probably put a pin somewhere along it, okay? But that's technically not appropriate. Okay. Any questions on these different types of beams? Yes?
So is it appropriate to say that a beam is technically anybody that is getting a transverse loading?
Yeah, and you know, that's, I mentioned the plates a few minutes ago. It's not, can't be, this table is not a beam, okay? Because it's got so much width to it as it's going across. Can I make some approximations? Sure, okay, but that's more of a plate. Okay, so here we're constraining ourselves to the idea that it's going to be small in the 2 other dimensions. Do things scale similarly, though? I mean, it's kind of like a beam, right? This tabletop, right? And it is kind of like you have simply supported tabletop stuff going on here, even though you have 4 legs. Okay? Yeah, you know, these principles are going to transfer over. But if I were you and I had to do something somewhat precise, I would probably, you know, maybe take a look at a few formulas out there for plates and loading. But once you get to something even as simple as a tabletop in today's world, we're going to run it through finite element, okay, because it's so accessible. Does that mean we're much less sophisticated than, say, the engineers from 50 years ago? Yeah, probably, okay? But, and you know, you can debate, did they have better engineers 50 years ago or now? I mean, you don't know. We have engineers with different tools, but hopefully we have good engineers that were using the tools that they had at the time, right? That's what an engineer is, doing the best that they can with what they've got. And they did amazing things. Amazing things. If you think about flight, especially in aerospace engineering, it's just absolutely amazing to see what they did. Okay, so section of a slender member. There is a member. It is not that slender, given how I drew it, but you get the idea. Okay. So if we think of the internal loads here, what kind of you know, what could we be talking about? Okay, so what am I talking about? That's a very vague question. Let's imagine that this is one of my slices. You know, the way I draw my slices, right? Okay? And I'm looking at it, I just sliced the beam, and I'm looking at open face. What do I see if I want to think about the internal loads? What are my options? This is now not just transverse loading. I'll take whatever type of loading you can imagine. What would I see in that slice? Yes.
Shear.
Okay, so I could see shear. Very good. All right. So let's go one step further. Now I give it coordinate system. Okay. And yes, this is pre-programmed. All right, but but how would you, and we're not talking about stresses here, right? We're talking, there are only two types of internal loads we're going to discuss right now. One is moment, one is force, okay? So what would a shear force look like? And how would I draw a shear force here? Yes, so good. I would draw it parallel to the face, right? I would draw it something like this, parallel to the face, and maybe in the y direction, maybe in the x direction, maybe in some other direction, right? But I wouldn't draw it if it's a pure shear force. I wouldn't draw it in the z direction, okay? Assuming this slice, okay, is in the xy plane. Good. All right. What else? What else might I draw? Yes.
You might draw the axial force acting
Yeah.
in the z direction.
Oh, in the z direction. Okay.
Say the cup was in the xy plane.
Yeah. So I would say if it's acting, okay, like that. All right. Yeah. Okay. So I would say that is, okay. I will renege. I meant the plane is in the YZ plane, not the XY plane.
In that case,
All right. So yeah. So you're right. Okay. You're right. Touche. All right. You're right. So we're talking these shear forces would be in the Y and the Z direction. I'm sorry. Okay. So when we do all those fancy things, okay, they're in the Y and Z directions, not the X directions. Sorry about that. Okay. So now, give me another thought. I know you have another thought.
So you have the axial force acting in the X, shear, Y, and Z.
Yep.
But you would also have moments about each of those axes as well.
Yes. All right. So I could say that this would be an axial load, right? That's in the direction of X. Okay. And you're also getting at something where I could have torques, okay? I could have moments that are causing essentially bending or twisting. So the way we think of like X, if you think about a torque here, about X, what is that? That should look something familiar, right? That's torsion. That's just twisting this thing like we've been doing. Okay, if I have that. So that's this one. What are Y and Z? Think back to your statics. What are they really? Yes.
Bending.
Yeah, those are internal bending moments. Okay? We're not drawing the nice 2D diagram here, right? But if I were to slice this thing, right, like this, okay, this could be, and I say that Z is coming out of the board, right? That's just an internal bending moment. You see, that's like that's this one right here. Okay. And then this one is about Y, is an internal bending moment about the Y-axis. Okay. So, very good, very good. All right, so let me just put up the pre-programmed thingamabobber, all right? But I will add that, yes, the slice shown is in the YZ plane. Sorry about my mistake. Won't be the last time this semester. Okay, so we got axial force, Fxx. We've got our shear forces, Fxy and Fxz, right? So we're saying, okay, it's that's not right. See, we've already seen this. Okay. I remember these orders do not matter too much, right? But what we're saying is that this is the Z. No. Oh my goodness. That's the X face in the Y direction. That's correct. And this is the X face. This is the X face in the Y direction, and this is the X face in the Z direction. Okay, those are shear. So those are our shear forces. We can have a twist, all right, which we call MXX, right, or MX if we would like, and that would be similar to the torque that we've seen. And we can have our bending moments, MXY and MXZ, like that. Okay. Any questions? All right, thank you. So, what's happening inside the beam? We can have varying internal shear forces. We can have varying bending moments. Okay, so this is now jumping to the idea that we're dealing primarily with 2.5D structures, and we do not have twisting. Okay, so we're saying no twisting. Okay, and we also do not have no axial loading. Okay. So here, what you did before, using the convention from Hitler, right, is you would draw an internal shear force, which we give by V, and an internal bending moment, M. And it's important to try to get the convention straight so that V is down this way and MB would be going up like that. Okay, and yeah, we could have an axial, right? But let's just say we're not thinking about that right now. Whoops. Okay, and that's about it. Any questions on this? Convention, we've already talked about this a little bit, right? In terms of if you have it open to the right, then V is downward. If you have it, and we'll do this again, it won't be the last time, right? But in this case, right, V is up and M is this way. Good? All right. So Crandall, Dahl, and Lardner also have an approach to beam bending problems, right? We've talked a little bit about Crandall, Dahl, and Lardner's approach to static problems, where we have equilibrium, geometric compatibility, and constitutive relationships. If we look at CDL, they also essentially have a 3-step process for handling just equilibrium. Okay? So you are going to create the model, and that's you kind of almost, I don't know, that's you want to do that, right? Identify the actual problem. And actually, this is not super trivial in that, so as we were undergoing our ABET accreditation, one thing that ABET wants us to keep track of is certain student outcomes, and there are 7 student outcomes. The first student outcome, okay, and if you look at it, if you look at the syllabus, I know many of you are probably like, what? Okay, but if you look at the syllabus, you'll see that there are some different student outcomes listed. And the first one is the ability to identify, formulate, and solve complex problems, complex engineering problems. Okay, so this goes right along with that. We want to go ahead and we want to create, we want to identify what the problem is. Then we will use external equilibrium. Okay, so we've talked a lot about this. And then we will use essentially method of sections. So these are not earth-shattering approaches to beam bending problems. Okay, I think you've probably already used them in the past, okay, but this is just a reminder. So creating a model might look something like making a drawing, putting a load on, doing a better job of describing your coordinate axes than I've done here. Okay. Then also putting forth what the corresponding external loads would look like in terms of vectors. And then we can move on to external equilibrium, where we write out equations. So we know that R and P are going to be equal to each other here. And we can then select a location about which we take the moments and submit and set them equal to 0. So in this case, I've gone ahead and specified this point O, and that's where we're taking the moments, and that we have here, right? You've seen this a lot of times before. And then in terms of sections, we take a slice and we look at the internal shear force, V, and the internal bending moment, just like you have here. Okay. Any questions about that? Any insights that you might have that would shatter my world? Does anyone like beam bending problems better than other types of problems that we've covered, like torsion? No? I don't know. I think I like beam bending problems better than torsion problems, to be honest. But that's just, maybe it's just me. I have issues knowing which direction we're going. Okay. All right, and yes, we can go ahead and we can solve for the internal shear force, V, and we can solve for the internal bending moment. Okay, and we'll do more of this in the future, but you've been familiar with creating those shear force and bending moment diagrams, right? Where you say how the shear force is varying across the beam, right, and how the bending moment's varying across the beam. Yeah, this is just getting us started. Okay? I mean, we do have a nice expression for V, okay? And we do have a nice expression for M, and in this case, right, they just happen to be constant. So that's very nice. All right. So here we go. All right, we have an origin and a positive direction. We might have discontinuities along the beam, and that could be from a distributed force changing, could be from a point load being applied or concentrated force being applied, and you can also have these moments that could be applied to the system. Okay. So here's kind of an example where if we're going to draw out what's happening across the beam, it would look something like this, like such. All right, we've done these before. All right, and we'll go into more depth. All right, this is just going, this is just giving us a little familiarity with what it looks like. Okay, like this. Okay, now. Dudes and peoples. No, you cannot do it this way. No one told me that was wrong. I was thinking about it though. All right, so, goodness. All right, so here, let's do the sum of the moments about O equal to 0, right? So if we have this, all right, if we do it at O again, what we're going to have, okay, is V and M and MR, right? So MR, let's say that's positive. So we have MR positive. We have a minus XV, right? That's going to be negative. And we have a plus M equal to 0. Okay. So in this case, M is going to be equal to MR, whoops. M is going to be equal to XV minus MR. Okay, MR is PL, V is P. So we have PX minus PL, and this is just going to be P times quantity X minus L. Okay. No one, that has been out there for a while, and no one's corrected me on that issue. All right. Blast. Okay, so that's how you would describe the moment, the internal moment, as it varies, as it goes across. So So like when I said that word and I looked at it, it said the moment is constant. No, it's not constant. Okay, not across it. All right. So sign conventions. Well, the distributed force, what are units of distributed force? Yes? Yeah, newtons over meter, force per length, right? Thank you. Okay, so what we're going to look at here is saying, hey, you know, there could be some delta F's between, say, this spot and this spot, right? So over some finite delta X, right? And then we're going to say, we're going to make that delta X smaller and smaller and smaller. And so that limit's going to go to 0. And that's what we're going to find as our distributed force. Okay. Now, distributed force W could be a function of X as well. And we're going to define it as being plus or positive when it's in the positive y direction. Okay. So positive W when it's in the positive y direction. You know, maybe some conventions here. We're already familiar with it. Typically, we take a slice and we have an axial load on that bar. Then it's going to be positive when it comes out in the x direction. And so if we took a slice and we go in the other direction, then we have positive like this too. So when we have the opportunity to look at a slice, all right, and we have our moment, okay, that we're thinking about, which direction, right, is z? Well, x cross y. X cross y comes out for this left one, right? And then here, right, x cross y would go into the page. So that means that, you know, this z is going to be here. So what we typically do, though, is we define a moment that's positive according to this scheme. You'll see that other people have other conventions. Okay. And I think I've mentioned it before. When I was taking this class, and actually CDL's book uses a different convention than the book that's suggested for the class, which is Hibbler's. Okay. Similarly, or dissimilarly, all right, with V's, I don't have a very good way to kind of remember how those go. Okay, but we do define V to be positive when it's going downward, when we cover up the right, okay, as Jeff Hansen says, and we define it to be positive upward when we cover up the left. So these are the conventions, and we hinted at them earlier. And I think I've said it before, I was confused by CDL and Hibbler's disagreement when I started teaching the class. Okay. Now, these are two equations that you want to have. We'll talk about them today. We'll kind of derive them. Have you seen, you did these before or no? In statics, do they give you these equations? Yes, no, maybe, yes, good, okay. So, we'll go on to kind of explain how these come to be, but these are two that you definitely want to know. So what we're saying is that the shear force, the derivative of the shear force with respect to x is going to be equal to a distributed load, and the derivative of the internal bending moment with respect to x is going to be equal to the shear force. So here's a distributed load, W, and then we take a little section, right? And it looks something like this. All right, so what in the world do we just do? See, that's a distributed force that we said is W, and it's positive. This is a beam, that's the green part, and then we're saying, let's just take a chunk out of that beam. And that chunk of the beam is going to have some width, delta x. So delta x down here. And we're going to say on the left side, I can describe some internal shear force, okay, V, and I'm going to draw it upward because that's the convention, right? I've covered up the right side, or the left side, covered up the left side, so now I have to draw it upward. Covered up the left side, and so also I will draw a bending moment, okay, that gives us a smiley face, right? That's how I look at these internal bending moments. I have a distributed force applied to this chunk, right, like this, and we have our right side now that we will also say has some shear force on it, and we'll also say that it has some bending moment on it, and it's going to be a little bit different. Why? Because that delta x is on the small side. So when we do that, when we've got that small amount of change, okay, we can say we don't know what it is right now, but we're going to try to figure it out. Okay, we're going to figure it out by using equilibrium. So what do? We say the change in the y direction for the forces internally is going to be equal to 0. And so we can say that we have V plus this delta V, all right, like that, okay, acting downward. We can say we have the V on the left side acting upward. And we can say that this distributed force, W of x, acting over delta x is just going to be Wx times delta x. Okay, that's all. Let's do some of the algebra. We have here some simplifications, right? V minus V is going to be equal to 0. You still have a delta V, and we have our Wx times delta x. That's equal to 0. We can write that delta V over delta x, all right, now right down here, is going to be equal to W of x. And if we take the limit as x goes to 0, right, that just becomes the derivative. So we're saying that dv dx is equal to dw. Okay, that's it. So that's how we derive the first one. When we say first one, this was the equation that we had over here. Okay, so that's the derivation of this one. Let's look at the derivation for the one on the right. So we have the summation of the moments at a location O, specified here. And we'll say, all right, well, we've got m plus delta m. That we'll say is acting in the positive. We'll say this is acting in a negative direction. We have, someone want to explain, where did this come from? What is this? What is this term? What do you think? Yes?
The distributed force over delta x.
Okay, so which part is the distributed force over delta x, and what does that mean? Yes? Okay, I understand that. So how is this moment calculated? Because this is a moment equilibrium. So you got it right. But you want to say how it was, what's going on here? Yes. Okay, shear force times length. All right, so there's not a shear force written in here. Okay. All right, so okay, so you're saying the derivative of the shear force, you're plugging this into here. That's interesting. That's interesting. Without looking at what's on the left side, how would you describe that equation? Like, where does the 1/2 come from? Like, what is that equation doing? What is it? How do we? All we're doing here is we're applying equilibrium. So my question is, where in the world did this come from? Yes.
It's the distributed force. That's like half the from delta.
Okay, all right. So, yes. This right here is a force. What is that force? That's the force that W of x, or W, is applying over this entire width. Okay? But we need a location, right? Or we need a distance. We're doing this summation of moments with respect to O. Right? So that force is effectively acting halfway across. Like you were saying. What was your name? Raymond, okay? So as Raymond was saying, it's halfway across. Right? So this is just the distance, okay, to center of, you could think of it as center of pressure, right? Or center of applied concentrated force. Or distributed force. That's probably better. Center of distributed force. We'll do that one. Center of distributed force. Okay. And then, where does this one come from? That one's simple, yes? Right, shear force on the left, and that's the distance delta x away. Okay? So that's how we do the equilibrium of the moments, okay, on this chunk. Now we do a little bit of algebra. Okay, we see that we have a delta x times a delta x. So even though I made a big dealio about this, its contribution is going to be small. Why is it small? Because if you take a small thing and you square it, it becomes a very small thing. Okay? So that's what happens there. So then we're just left with these two terms, delta m minus v delta x, delta m equals v delta x, and that is going to be our relationship. dm dx is equal to v. Okay? So those are the big two relationships that we can use when we're looking at solving for internal forces in beam and internal moments in a beam. Okay. Any questions about this? Okay. So let's look at what these equations, both of them, mean in English. Okay. It means that the slope of the shear force V as a function of x is equal to the distributed load W at x. All right, well that's nice. I mean that's nice, but that's also not. I don't know. It's those are just words, and if you said that to someone on the street, they would not look at you very interestingly. Okay. Or they would look at you interestingly and then walk away. Awesome. Okay. What does this mean in the context of? Whoops. This is not. It's all going back. Okay. Well. Okay. Yeah, we'll just put it in English, but okay. We'll talk about that. All right. The second equation in English is slope of the moment m as a function of x is equal to the shear force of v. Okay. So if now we draw the moment. Okay. All right. So this let's go back here. This is a system that has a quadratic. Right? And if this is a quadratic, it's a second order polynomial as a function of x. If I take the derivative, so this is moment as a function of x. If I take the derivative of a quadratic, something with an x squared in it, or a minus x squared as is the case here, I'm going to get something that's just a function of x, right? The derivative of x squared is 2x, right? So what this is saying is that the shear force is the derivative of the moment. So we can begin to look at what's happening here and say, okay, this is second order, and then it goes to first order. Now, wait a second. If I have shear force and I take the derivative of it, and this is first order, what does the derivative of first order expression become? Yes? Yeah, it becomes a horizontal line, right? Or it's a constant, right? Often equal to 0, but if it's an indefinite integral, well, yeah, or it could be any constant, right? The derivative of any constant is going to be equal to 0. Okay. So, or the integral of any constant besides 0 is going to be first order. Okay. So what happens here is that when you take the derivative of this, it has a negative slope, and that corresponds to the distributed force. Okay. So we can go up and down here. We can start by looking at a system that's an actual problem, okay, where we have a distributed force, and we begin to think, oh, wait a second. If I take the derivative of something, all right, what would that something be to give me this horizontal line? And that's the derivative of the shear force. Another way to say that, if I take the derivative of something to get me a constant, that's the same thing as saying, if I integrate this expression, that will give me v, right? So you can start to see here that we can do a little thing where we say, oh, dv is equal to w dx, and I integrate both sides. Now, let's look at it exactly like that, okay? If I have a shear force and distributed force, I can take that equation and I can say that dv is equal to w dx. And then I can integrate, say, between a and b, all right? And I can get some type of expression for v, all right? So this is just putting this out there, okay? And same thing with bending moments. I could take an integral of the shear force between a and b, all right? And that's what we could say is a delta m, which is this integral of that. Any questions on this? This is starting to approach something that maybe is a little different perspective than what you did, okay, when you did these problems. Because what is the default? I mean, let's be honest with ourselves. If someone hands me a beam bending problem on an interview, which I hope they don't do, I don't plan to do that kind of thing. But if they did, right, how would you do it? Are you going to sit here and do these integrals? You think so? I think I'm going to just do equilibrium on the beam, right? That's how a lot of us would do it, right? Because these expressions are true, all right? I mean, depends. But at this point, what you're going to do, what you would probably do, all right? If you would do essentially what I just did wrong, but then I saw was needed to be corrected, right? All the way back here, right? This is how you've done it. When I say this right bit right here, okay? You can get V and you can get M by free body diagrams. Okay? You don't need this fancy dancy new calculus based approach. But there are cases when the calculus-based approach is useful. All right, and so that's what we're going to try to get across today. Any questions on this so far? Any thoughts? Can we see that you can do what you did last semester, all right? And if you're trying to do something quick, that's what I would suggest that you do. But if it starts to get complicated, or there's a distributed force involved, okay, then you want to use these types of newer relationships that we're describing. Okay? Now, using this information, right, we can say, oh, look, it's the integral of this function w, just happens to be a constant, and it's a negative value, so it's going to have a negative slope. And we are going to be able to write out that the integral of that is going to be a slope line. How do you figure out what this value is and what this value is? Well, we'll talk about that, but that involves using boundary conditions, because this is essentially an indefinite integral. Okay, so you need something to kind of set your constant, your plus c as it is. Okay, and then taking the integral of this, all right, is going to give us a quadratic. All right, and again, you would want something for the boundary conditions. And again, we'll talk about how to do that in the future. Okay, so here is the future. Here's the methodology. Step 1, you want to calculate the external loading first. You want to get the values of shear at the ends of the beams, and then we're going to establish the moments at the end of the beams. Step 2, use the differential and integral forms, and you can get a shear diagram and a moment diagram. Okay, so what are we talking about? And right, when we do the external equilibrium, don't bother with the distributed force. Figure out, right, where that effective force is and use it at its appropriate location. In this case, that's halfway across the beam. Then, after we've got these calculated, all right, so now I've got my effective force, W naught L. I have my moment at the left side. Okay, that's a reaction moment. Sometimes people will put MR, M sub R, but I didn't, okay, because it's acting at, we'll call A. We're calling that point A. All right, and then, okay, now I've got these reaction moments, or reaction moment and this reaction force, better said, okay? And I am going to draw, I want to be able to use this nice new handy-dandy expression that I've got, which is that dv dx is equal to w. Okay, but I don't know exactly where to put things. All right, so here is my integral. Okay, v is equal to integral w dx plus c1. All right, and so what is w? W is, well, it depends how you define it, but w is just a constant. It's a w naught. All right, and you could say that w naught is a negative value. All right, if you want, because it's going downward. Okay. So then when we do the integral of this, what we get is that it's w naught x plus c1. And we can say at x equals 0, all right, we have v is equal to w naught L, and at x equals L, v is equal to 0. Now, how do we do that? Okay, how in the world do we do that? This is how you do it, okay? You say, all right, I've got, to figure out what, well, I've got my external equilibrium that I've drawn out here. I figured out what R and MA have, right? So MA is this, and R is that. Then what you do, okay, for the right side, okay, you say, I am going to just take a little bit of slice here, okay, and I'm going to expose the left side, and then I'm going to use my convention for V and my convention for M here. Now there's a distributed force acting on it, Well, that distributed force right up to the right side, is nothingness. I think this point, I think maybe we should, if I can. Let's go ahead and let's move the front up. Oops. No. Doesn't work. Oh, okay. Nope. That's not good. What in the? Okay. Well, I'll just create. I think I'm going to create a new. I'll create a new slide here because this is. I think I'm going to lose people here. Okay. This is the distributed force. This is the beam with external loads drawn. Okay? And the way we did it here is that we said that we had R and MA. So we have R and we have MA, like this. Okay? And we can say that, okay, there's an effective force here, sure, that's fine. Okay, what I'm talking about is trying to figure out what's happening at the boundaries. And this is going to be something that you do over and over again. Boundaries meaning what's happening at the left side? Internally. And what's happening on the right side? Internally. Okay. So, for this, I would draw a little slice, okay, at the left side. And this is going on the left side, it has an MA. And on the left side, it also has an R. And if I use my convention, I have an M. And if I use my convention, I have a V acting downward. Okay? And what I'm saying is that it's a slice that has essentially virtually no space left side. Okay? So there's no distance. There's no distance essentially there. And I want to know essentially the M internal left side. Okay? And I want to know the V internal left side. Okay? And this is another way of saying if this is the X direction, this is just saying what is M at 0 and what is V at 0. Okay? So what is that? What is M of 0? What is V of 0? Well, usually the forces are easier to do first, okay, but it doesn't really matter. So what is M? What is V of 0? There's no, you don't have to use any calculus here. I'm just saying look at the diagram. Use it as a free body diagram. What is it? Yeah. No, it's not 0. It's all equal to R, right? Look at the diagram, right? You have an R here. This is why we're doing this, okay? I'm glad you said what you said, okay? Because the R is causing there to be a force on the system, right? And now this is going to be equal to R. Okay? What about M of 0? Do you want to, with your hand? No. Okay, almost. It's minus MA, right? Okay, why is that? Because we have, if you do the equilibrium here, right? This is saying that we have MA plus M is equal to 0. So M has to be equal to minus MA. All right? This is an extremely important thing to be able to do because we can do the integrals, but then we're going to be left dangling because we don't know what's happening at the left and the right side. Okay, okay, so now we got the idea. We got the name of the game, right? So what's happening on the right side internally? Tell me what to draw. Sometimes people think you should just give an exam at the beginning of the class to see how much people remember from statics. Instead, my philosophy is let's try to remind us what's happening from statics, right? So what would I draw on the right side? Are you raising your hand? No, you're scratching. Okay, that's fine. Do you want to opine? Yeah. Okay. So I'm going to have this kind of drawing, right? Okay. Now, what do I do for the internal loads? Okay. Yeah. So I'm going to have a V like this. Okay. And then I'm going to have an M like this, right? So that's the question. Is there a reaction? Is there external load here? You say yes, but no. Why would I say yes, but no? Yes, but no. Yes. Yeah, there's a distributed load, right? Right? There's that little distributedness going on here. Okay? But what is the length over which that distributed load is acting? It's 0. Okay, so that distributed load has no material on which it can act and do anything. Okay, so now your math answers apply. Okay, so now V is equal to 0 and M is equal to 0. Okay, for this type of situation, because there's nothing else acting on it. All right, any questions on what we just did here? Okay. So why is this important? Why is this important? It's important because we need to set up, yeah, we need to set up, okay, so I guess we should, right, we did this earlier, but, you know, I said it's just minus MA and R, but you have to solve for those, okay? The MA, well, we can do it, right? The MA is just going to be F effective, right, times what? L over 2, right? And what is F effective? Yes, I see W not L, right? All right, so MA is just W not L, and then it's times L over 2, so it's like that. Okay? All right, and then R, okay, is V, all right? But V is equal to, right? R is equal to F effective, right? And F effective is just W naught L. Okay. Any questions on that? We're good? All right. So once we have those boundary conditions appropriately laid out, okay, we can go ahead and start to draw these diagrams. Okay, so you see, I know that this is got some slope to it, and it's got negative slope because, well, W naught is negative here, all right, because it's in the downward direction, so it's a negative slope. So the slope here is just minus W naught, or yeah, the way this is defined, yeah, W naught, sure, okay, and it's going downward, all right, and this is just 1, and it's got to be up at W naught L, okay, and when it gets over here on the right side, we already said that V is equal to 0. So if you're drawing these out, the integral tells you what the shape of the graph will look like, okay? But the boundary conditions tell you what's happening at the left and the right. Okay? Similar here, right? M of 0 we said was minus W naught L squared over 2, okay? And then it's going to be equal to 0 on the right side. Okay. Now, what happens when you encounter a concentrated force along the beam? Usually some amount of increased anxiety on my part, okay? But other than that, once you know how to do it, it's not that bad. Okay, so here's an applied force across a beam. And now we'll go ahead and we'll just break it down like we did before, okay? So we have our force, we have our internal V, we have our internal M, we have our V plus delta V, we have our M plus delta M. We look at the effect of the concentrated force in the equilibrium, on the equilibrium. So we have V, we have minus V plus delta V, and we have now a new plus F. And we look at its effect. Well, okay, so that means that delta V is equal to F. And then we look at its effect on the moment. Oh, God! Okay, I didn't do that part of the derivation. Well, anyway, when you do that part of the derivation, do you see that you're going to have, for a moment, and let's just say we put it over here, you see that for a moment, you're going to have a F delta X, all right, over 2. And that is going to end up being a small amount, all right? Because you're gonna have, you have M plus, you have, okay, let's do it out, right? So we do the summation of the moments. We have a minus M, we have a plus M plus delta M, okay? And then we have this minus F delta X over 2, and that's going to be equal to 0. Okay? So what happens is you have delta M, okay, is equal to F delta X over 2. And since this is a small quantity, all right, I mean, it's not like delta X squared like it was before. We usually say that this delta M is going to be, the change is about 0. This is how we do it. All right. It's not significant change in the moment, so we ignore it. Okay. So the equation that you need to recall is that delta V is equal to F. Okay. So if you have now, I don't have an example, but if you have a shear force diagram, like this, what happens is that when you get, and let's say that you have a concentrated force applied in the middle, like this, okay? When you get to that, let's just say it's down here, and then it gets to this point, and then it goes like this. This would be a delta V equal to F, just like that. Okay, that's a jump. It's a discontinuity. That's why it causes anxiety. So discontinuity in the force but it doesn't cause a discontinuity in the moment. The region of a coupled moment. When you have a moment that's being applied, okay, then we have something that looks like this. Now, if I said that y was in the vertical direction, which direction would z be? Y is vertical, right? Z is coming at you, right? Yeah? All right, so right hand rule, like this. Yeah. Coming at us, right? Okay, so is MAP positive or negative? Well, it looks kind of negative, all right? So this is one of the weird things. When you pick a convention, you have to stick with the convention, all right? And sometimes that sticking with the convention means awkward things happen. And this is one of them, all right? So when you see the MAP, and you see it this direction, you're like, oh, that's going to be a negative change in the moment. No. If you go through the derivation, which we'll just put up here quickly, the change in the moment, okay, at that location. So if I'm looking at a plot of my moment as a function of x, all right, this would be a jump of like delta m. That would be MAP. Okay, that's the jump from here to here. Okay, that's a positive. And it's also very important that we keep in mind that this is going from the left to the right. We'll go through more problems on this in the future. Okay, but this is because you could say, oh, if I go from the right going left, I do a positive, then it goes the other direction. No, this is coming from the left going to the right. Okay, this delta m is equal to MAP, all right? And this MAP is actually what we would normally consider to be a negative moment being applied to the system. Okay. So negative, or the MAP, which is by convention defined here kind of in the clockwise direction, if it's going into the board, which is opposite of the z direction, it causes an internal jump in that moment, that's positive. You know, this is also probably a good time to take attendance. Yes, I understand. But it's also probably a good time to just point out that we're talking about relationships between external loads and internal loads. Okay? So like this region of a concentrated force, that's an externally applied force, but it has an effect on the internal force, internal shear force, right? The externally applied moment has an effect on the internal bending moment, okay? You're not going to be able to describe, or you're not going to be able to see the internal bending moments, the internal shear forces, right? But what you can get a feel for is the external loading that you apply. And we're trying to figure out what the invisible essentially is doing. Okay, so which of the following relationships is true? This one is true. This one is true. This one is true. This one is true. And the other two are not. Okay? All right, we've gone ahead and we've looked at how to do these types of problems. There will be more to be done. That's all you have to do. Blah, blah. All right, let's get you the attendance so you can get out of here. All right. Any questions while I'm posting the attendance?